Today I kind of wanted to shed a little light on why RTDs have 2, 3, and 4 wires on them, and we'll get some of the details. But first, I kind of wanted to start out and just have some, just a brief summary of an explanation of why they do this. An RTD is just, in its simplest form, it's just a resistor made with platinum wire. That's the most common version. And when we add lead wires to that, we're adding resistance to that circuit, and we need to get rid of that resistance, so we're measuring just the resistance of that platinum sensor. And a couple different ways to do that. You can add a third wire to that circuit, and even better yet, you can add a fourth wire, and that will completely eliminate all the resistance, lead resistance, out of that circuit. 3-wire RTDs, they work okay if we're not running a very long distance. Their ability to eliminate the lead resistance is dependent on each of those 3 wires having exactly the same resistance, and that just isn't the case. There's always some variation, so there's going to be a little bit of an error that comes into play there. 2-wire RTDs are typically used in HVAC systems, along with they'll have maybe like 1,000 ohm RTD, and that helps make that series resistance that we're adding a smaller percentage of the total resistance in that circuit. So the error is not quite as large. And it's always a good idea to use shielded wire if there's any possibility of any interference in either 3 or 4 wire circuits. Those circuits don't do anything to help eliminate that. You really do need to use a shielded wire if there is electrical or radio frequency noise around. And then with a 3-wire circuit, it's good to eliminate or minimize the length of lead wire that you're using. But if you can't do that, it's a good idea to plug a transmitter somewhere into that line closer to the RTD. And so that's kind of it in a nutshell. And I'm just going to go through a little background stuff now, and then we'll get into a little more detail on how each of these 3- and 4-wire circuits eliminate the lead resistance. First off, the manufacturers follow some standards. That's an ASTM or an IEC standard. And you probably heard the Class A, Class B RTDs. And these are the equations that define the tolerance that that platinum element is trimmed to at 0 degrees C. Each one of these equations, if like for example, if we have a Class A RTD, it's an IEC 60751 standard that it follows. We can take that equation, it's 0.15 plus 0.002 multiplied by the temperature in degrees C. So whether it's above or below 0, drop the minus sign if it's a below 0 version. And that'll give you this interchangeability tolerance, or the tolerance that that sensor was trimmed to at 0 degrees C. We can look at that a little better on a graph form. And you can see here on this graph, this is right where all the lines converge at 0 degrees C is where they trim those. So we're going to have the tightest tolerance there. And as we move away from 0 degrees C, the tolerances expand. And they will diverge both in the positive and negative directions. And if you look at this graph a little closer, you can see that the ASTM standard has just a little bit tighter tolerance than the IEC standards when you move away from 0. At 0, they're the same. So when we build these sensing elements, and if you were to add a 2-wire circuit to it, you're going to be adding series resistance to that sensing element, and that's going to throw off the measured accuracy reading for that sensor. The one way to eliminate this is just to add that third wire. And like I mentioned earlier, the ability of this to eliminate that lead resistance depends on each of these three conductors having exactly the same resistance. And unfortunately, they just don't. And so if we look at this circuit diagram here, we see that we have one of those three leads connected to one side of the sensing element resistor, and the other two leads connected to the other side. In a real simplified way of looking at the way that your transmitter or might be a chart recorder or a PLC, when they look at this circuit, what it's doing, it's measuring the resistance between the L2 and L3 leads, and then it will subtract that resistance from what it measures between L1 and L2, and that way it ends up with just the resistance of that sensing element. And that's not exactly the way the electronics work, but that's just kind of a real simplified way of looking at it. And if you wanted to check the RTD yourself with just a regular 2-wire ohm meter, you can do this manual lead wire resistance elimination by just measuring L2 and L3, which in our lead wire case would be the two red leads, and then subtract that from what you measure between one of the red leads and the white lead. And that way you'll get just the resistance of that sensing element. And here we look at the effect of the lead wire on this interchangeability tolerance that we talked about. If we look at a grade A, for example, with 22 gauge wire, let's say it was trimmed, exactly to 100 ohms, you could get away with about 15 feet of 22 gauge wire without affecting that initial interchangeability number. And you can see as the wire gauge size, the size of the wire decreases up to like 30 gauge, you can only add 2.2 feet. And of course, these numbers all depend on kind of the worst case scenario, with the three leads being at the maximum ends of their tolerances for resistance. But anyway, it's just an example of how adding this lead wire with a 3-wire circuit can really throw off the accuracy of that RTD. And so you really need to be aware of that and eliminate the long lead wire runs whenever possible. If we look, about 0.04 ohms is about 0.1 degrees C error. So if we were to measure each of those three, the resistance of each of those three lead wires before they're put into the sensor, and if you have, like a 0.04 ohm variation, if you hook that up, you're going to have a 1/10 of a degree C error. And some of the testing we've done, it doesn't take much to end up with that 0.04 ohm variation. If we look at just a simple example here using 22 gauge, 0.016 ohms per foot, and just in a 10-foot cable, we end up with a 0.04 degrees C error. And stepping that up to a 30 gauge, 0.26. So pretty dramatic when you go to the smaller diameter lead wires. What can we do with a 3-wire circuit? You can add a transmitter closer to the RTD and shorten up that cable run. What we do, and I think other manufacturers probably do, is that we actually balance the resistance in each of those three leads. So if we have a sensor that has 50 feet of cable on it, 22 gauge, we know that that sensor is not going to pass calibration with that much cable on it. So during the manufacturing process, we take that cable, measure the resistance of each of those 3 leads, and then add a fixed series resistance to the 2 low ones so that it matches the highest resistance lead. And we can get them pretty close that way, and we can have that sensor now with that 50-foot cable actually compensates correctly for the lead resistance with a 3-wire circuit. Much better way to do this, of course, is to have a 4-wire circuit because they fully compensate for their lead resistance, or if you have a connector in line, any pin and socket variation resistance, it's going to compensate for that also. And it's just the best way to get the most accurate measurement out of an RTD. And, some through the a little different circuit design here, it's sometimes called current potential. There's also a Wheatstone bridge, which is used, circuit designs used kind of do the same thing here. And I don't exactly know how this works through the magic of electronics. Sometimes it does seem a little magical, but I think all that we need to know is that, yes, it does work, and it works very well. And if you have a PLC chart recorder, whatever that you're connecting the RTD up to, and it has a 4-wire input, it's really a good idea to get a 4-wire RTD and hook it up and get the best possible measurement out of that sensor peripheral assembly. Now we talked about adding a transmitter to shorten up a long lead wire run with a 3-wire RTD. We can also do what we call matching. So if we were to measure the resistance characteristics of the probe with the lead wire on it, whether it's a 3 or a 4-wire, we can take that information and plug it into the transmitter, and it will eliminate a lot of the interchangeability resistance. And then you don't have to be too concerned about whether it's a Class A or a Class B sensor. You can use, a Class B sensor. It's calibrated, or essentially what we do is characterize the resistance versus temperature relationship, come up with some temperature coefficients, and they get plugged into the brains of the transmitter, and then it mathematically says, okay, here's the resistance, and here's the corresponding temperature for this specific RTD. So that way you end up with about, roughly plus or minus 0.2 degrees C throughout the calibrated range of that transmitter temperature probe. Still need to, with a 3-wire sensor, keep the leads as short as possible. That still comes into play. And in the longer lead wire runs, the leads should be balanced so that, just as close as we possibly can get those resistances to match each other. So I just wanted to make sure that was clear, that matching does not eliminate the need in a 3-wire system to to just run any length lead that you need. It still needs to be a fairly short run. So with that, I think Tony, I don't know if there's any questions that we have yet. I'm going to...
Yeah, we do have one question here. and it is, what's the recommended maximum total length for a 3-wire connection?
Well, it depends on the size wire that's used. I know in our little example we had, there was with an 18 gauge wire, we could run about 60 feet roughly with a Class A sensor. Class B, you can get by with a little more. But, the errors are usually pretty small, and for a lot of industrial applications, you can probably tolerate a couple tenths of a degree C error. So just as a rule of thumb, I usually just use 250 feet for a 3-wire RTD.
All right, that's all the questions we have.
Okay, so just kind of a quick review here. And I guess it's just if you want the best possible accuracy out of a measurement system, go with a 4-wire RTD and make sure that your PLC, your controller, whatever this is being connected to, has that capability to have a 4-wire RTD input. And that's really the best way to do it. So I think one other thing I wanted to mention, if you need a little more information about this matching for the kind of best accuracy, we do have other videos on our YouTube channel, which if you go to YouTube and just type in RTDology, you'll get a whole list of webinars that we've done. Some are long, some are short, and covers a lot of different topics. We also have on our website some technical papers that talk about interchangeability, talks about matching transmitters to RTDs. And then there's also one there about balancing lead wires in a 3-wire circuit to maintain the best possible lead wire compensation. So I guess with that, that's about all I had for today. This is a kind of a real quick presentation here. Yep.
We got one last question just popped up here. Is there such a thing as a 6-wire? Can you just keep adding wires to reduce lead resistance?
No. If you see a RTD that has 6 wires on it, it probably is a dual sensing element. The only way to minimize the lead wire error in a 3-wire circuit is to use a larger gauge wire. So if you were to build an RTD sensor that had, like 10 gauge wire, really heavy stuff, you could run that for quite a distance before there would be a problem. Just when the lead wire gets smaller, that variation in resistance between the conductors varies the most. But you go larger with that wire, that variation is minimized.
Yeah, okay, that's it for questions so far.
Okay. Well, I think with that, Tony, I think you're gonna send notes out to all the attendees. Then send out the slides. Is that what happens? And then
we will send out a video version.
Okay.
Of the webinar. Yeah.
Okay. Sounds good. Then again, I guess if any other questions, feel free to contact us. You can hit up info@burnsengineering.com, and one of the applications engineers will get that and give you an answer. So with that, thanks for attending, and we'll catch you on the next one.